Welcome back to Maths with Mrs. J. We're ready now to start our series of videos about integration. What is integration? Well, another word for it is anti-differentiation, and that gives you a clue as to what it is. It is the opposite of differentiation. It is going back the other way. So you might start with a derivative and have to find the function. Now, why would we want to do that? In a practical sense, quite often what might happen is that we might know a function for acceleration with respect to time, and we might want to know what a function for velocity with respect to time is. Because acceleration is the rate of change of velocity, to go from acceleration to velocity, we are going to anti-differentiate or integrate. And then if we wanted to go from our velocity function to our displacement function, s of t, we will have to anti-differentiate yet again. Now, we're going to take this gradually. We're going to do it bit by bit. To start off with, we're going to be doing indefinite integrals. The main reason why we might want to do what's called a definite integral would be to find area between two curves, or area between a curve and the x-axis, or even taking that a step further and talking about volumes formed by rotating shapes around either the x-axis or the y-axis, or in fact any line that you choose to use. Let's start nice and simple. In order to integrate well, you need to have a very good handle on your differentiation rules. So each time I teach you an integration rule, we're going to start with the relevant derivative and see how we can work backwards from that. All right, so to start with, we remember that if we just have x to the n and we want to differentiate with respect to x, that n, that index comes down as a multiplier, and then we decrease the index by 1. We've done quite a few examples of those in our differentiation videos. So going back the other way, we're going to do the opposite thing. This is the terminology, or the way we write it. That's your integral dx with respect to x of x to the n. So what we're going to need to do is we're going to need to increase that index by 1 and divide by that new index. What's this plus c business here for? Well, we might recall when we were differentiating that if you find the derivative of any constant number, you're always going to get 0. So once you're anti-differentiating, there is this constant term that will come in. Sometimes you'll be given information in the question that will enable you to actually calculate what that constant is. But for now, we'll leave it just as a plus c. Let's do some examples and see how we go. Let's start with a fairly easy one. If we're looking at x, that's really x to the 1. So to anti-differentiate, I need to increase that index by 1, so that'll be x squared. And I'm going to divide by that new power. But we've already got a 2 in front. 2 in front divided by 2, they cancel, don't they? So we're going to get our x squared plus c. Let's just check. A great way of checking that we're correct is differentiate this and check that you get back where you started. Derivative of x squared is 2x. Derivative of c is 0. So we're all good there. We're perfectly okay, just like with our derivatives. If we have a sum or a difference, the integral is the sum or difference of the integrals. So we can do each bit. So x cubed, we're going to increase our power of our x to 4, and we're going to divide by that new index. This is really x to the 1, so we're going to need 3x squared on 2. If you have a constant, there's really an x to the 0 there, isn't there? So this will become 2x. And then plus our c. Again, we can check that we're correct by going back the other way, differentiating and checking that we get back where we started. This in particular will help you. 2x, derivative of that is 2. All right, now these remaining 3 examples, we're going to need to do a little bit of work before we do the integral. Let's have a bit of a look at this first one here. 1 over x to the 4th. Now we need to know enough about our index laws to know that that's the same as x to the negative 4. So that will be our first step. Once we've done that, then we can follow our normal rule. So we're going to increase that by 1. Now increasing that by 1 gets you up to negative 3. And we're going to divide by that. This will be a minus 7x plus c. Now that doesn't look great like that, does it? So let's just rearrange that. X to the negative 3 is 1 over x cubed. So I'd write that as negative 1 over 3x cubed minus your 7x plus your c. If you're given your question with positive indices, you want to leave your answer with positive indices. All right, we went via negative indices to actually work it out, and that's perfectly fine. Here we have a fractional index. If we have the cubed root of x to the 4th, that's the same as x to the 4 over 3. Now we are going to increase that index by 1. 4/3 plus 1 is 7/3. We're going to divide by 7/3, right? And let's just over here tidy that up a little bit. Dividing by 7/3 is the same as multiplying by 3 over 7. X to the 7 on 3, let's think about this for a minute. 7 on 3 is 2 1/3, isn't it? So we could write this as x squared cubed root x if we wanted to. We could just write it as x to the 7 over 3 if we wanted to. But because the original question had your radical sign in there, it's probably better to put it back as this. So plus your x plus your c. Let's have a look at this next one here. X times root x is really x to the 1 times x to the half, isn't it? So this is the same as x to the 3 on 2. Again, we're going to increase the index by 1, so that'll be 5 on 2, and divide by our new index. Don't forget our constant. Again, that doesn't look great, does it? Let's just rearrange that. So we're going to have 2 over 5 for starters, because if you're dividing by 5 on 2, same as multiplying by 2 on 5. X to the 5 on 2 is x to the 2 1/2, so we could do it as x squared root x. And because that's in a similar format to the way the question was given, that's probably the best way to give your answer.